All right, the next presentation is Rachael Pabst and Ellie Wolcott. Scalable in situ water extraction for lunar bases, a proof of concept system. One can be
Good afternoon, everyone. My name is Ellie Wolcott, and I'm a senior studying aerospace engineering here at the UASI.
My name is Rachael Pabst, and I am also a senior studying mechanical engineering here at the U of A.
Today, we'll be giving an update on our engineering senior design project, Lunar Automated Regolith Processing for Lunar. So as I'm sure many of us can relate to, people can't seem to stop talking about the moon. Just last month, we saw the first commercial moon landing by Firefly Aerospace, and in the next couple of years, NASA is going to put the first American woman on the moon with the Artemis mission. Lots of companies, both public and private, in the United States and across the world, are really interested in establishing long-term human presence on the moon in the form of lunar bases. This is going to require a lot of resources, though, from a launch pad, habitat elements, power, so astronauts can watch Netflix, and perhaps most importantly, water, drinking water. The problem is, the moon doesn't have any bodies of water the way the Earth does, and it definitely doesn't have any beaches. So now the challenge becomes sending drinking water from Earth to the moon. This is really expensive and really fast. To put it in perspective, it costs about $1,500 per kilogram sent into space, and 3.2 kilograms of water are recommended per person per day. So to sustain one person on the moon for a full year would cost just shy of $2 million. If you take that a step further and try to sustain a 100-person lunar base, that quickly climbs to almost $250 million. So what if there is another moon? As it turns out, there is. The moon has permanent shadowed regions called PSRs at its poles, and these are cold enough to sustain water in the form of ice crystals. This ice is dispersed throughout lunar regolith, which is dirt mixture that covers the surface of the moon, and it's made up of volcanic beads, impact glass, rock chips, and ice. For the past 6 months, our senior design team, some members who are with us today, has been working on a 2-unit system called LARC that will collect and process water from lunar regolith. This system is comprised of a mobile excavation unit, or MEU, a stationary extraction unit, or SCU, and it will produce at least half a liter of water in a 24-hour period. This may not sound like a lot, but this is just a proof of concept, and could easily be scaled up with more processors and more mobile excavation units. Even with current water reclamation techniques being used by the ISS today, in situ resource utilization could save upwards of $5 billion annually. But not quite yet. Like I mentioned, this is just a proof of concept, and our system is only going to work under Earth atmospheric conditions. But in future years, more senior design teams can take our work and adapt it to lunar atmospheric conditions and even incorporate automation, which is going to be extremely important in space.
All right, so next we just wanted to talk a little bit about the planned operation of our system, as well as give you a brief overview of both the mobile unit and the stationary unit. As you can see, our system will have 5 distinct steps that it goes through to process the regolith. First, the mobile unit will excavate lunar regolith from the surface of the moon. It will then load that regolith from the mobile unit into the stationary unit, where water will be extracted through a heating process. The dehydrated regolith is then unloaded back into the mobile unit, which takes it away elsewhere to be disposed of. So we're going to take a look first at our mobile unit. As you can see, we're using a bucket elevator as our excavation system. This was based on quite a bit of research by the team, looking at several other similar systems with a similar goal in mind, who very successfully used a bucket elevator for their excavation. The system moves up and down on a linear actuated arm, and our system can excavate at a depth of about 10 to 20 centimeters. But again, as Ellie was saying, this could be scaled up into a much larger process as needed. We also have a linear actuator controlled load bed, which carries the regolith around and can be tilted up to around 60 degrees when regolith needs to be offloaded. Here we have a few current progress pictures. Since these photos were taken, we have made quite a bit more progress on the unit, including finishing building and mounting the bucket elevator. Final steps for this unit include finalizing the electronics, as well as potentially printing new wheels that can better support the weight. And here we have our second unit, the stationary extraction unit, or SEU. As you can see, the regolith enters from the mobile unit through a funnel at the top of this system and passes into a heating chamber through an open ball valve, which is then closed. The heating chamber is wrapped in heating tape, which heats up to first melt the ice and then evaporate the water, which passes into a shell and tube heat exchanger to condense and drips into the removable water collection tank. The dehydrated regolith then passes through a ball valve, which is opened at the bottom of the system, back into the mobile unit. Here's a progress photo from our stationary unit. Similar to the mobile unit, we have made significant progress since this photo was taken, including mounting the condenser system, as well as putting it on a frame. Final steps for this unit include wiring the ball valves so that the system can be run automatically. Finally, we wanted to talk a little bit about our Regolith simulant and the process of how we got that. Since our unit will likely be operating at the lunar South Pole, we used LSP2 or lunar South Pole Regolith simulant as our model. To collect the simulant, we traveled about 45 minutes south to the San Javier mine, where we dug up our simulant and brought it back to the university. From there, it was baked for 24 hours in small batches to dry it. This allowed us to more precisely control the water content to match the current estimates of the weight percentage of water in regolith on the moon. After it was dried, we put it in this machine you can see here called a rototap, where it was shaken around to sieve it for about 10 minutes. This led to the final product, which was a smaller grain size, which we used as our simulant, as well as some larger chunks, which were discarded. The grain size distribution of our final product does very closely match the grain size distribution of the LSP2 simulant, which is important since it will react similarly to both heat and water exposure, which are both very important in our project. Looking forward, we will be testing both of our units at the San Javier mine coming up here in the next few weeks, and we will be presenting our final project on the mall at Senior Design Day on May 5th. And if you're interested in seeing the final product, you're more than welcome to come check it out. Thanks for listening, and we'd love to open the floor for any questions you might have.
Questions?
How do you envision your apparatus to function on the lunar surface with a reduced gravity? Is there any design changes that you would make?
Sure. So we did at the beginning of the year do some analysis to make sure that our system would at least be changeable so that it would work on the lunar surface and they wouldn't have to completely start from scratch. I think there might be some changes that might need to be made with the processing system in particular, since it is so dependent on having water vapor that's able to form and not just like form right back into ice inside the condenser. But I think that based on the research that we did earlier last semester, it will definitely be adaptable to lunar conditions.
Another change that we could foresee other groups making is changing out the wheels. So we went with tires, just for budgetary and schedule constraints, but some of the early lunar missions with the Apollo missions used mesh tires that can't pop the way that rubber tires can. And so that would be something that may be a little bit more durable and would require less maintenance. Any other questions? Yes.
How much does a unit cost?
So our budget for this this project was $4,500 for the whole thing. Obviously, a unit with space grade materials would cost much more, but since it's just a proof of concept, it's a bit cheaper than a real one would be.
All right, how much would it cost to send a unit to?
So that would depend heavily on the materials you're using. It costs about $1,500 per kilogram sent into space. We haven't weighed our unit because we're not done building it yet, but that would depend on the materials that are used, and things like using mesh wheels instead of rubber would pose different weight constraints and like that. Great, thank you
All right.
guys.
Thank you.